Another process is called free-forming. And in this case, we don't even use a mold. Think of, we talked at the very beginning of airplane canopies. Think of how those were made. You'd have an opening in the shape of a teardrop. You'd have, say, metal around it and an opening in the center, and the plastic would be blown from underneath it and blown through the opening, and that plastic would be formed, the shape of it would be formed by that, what the shape of that opening was. Kind of like that bubble we showed the previous one, except, say, if it was an airplane canopy, the old World War II airplanes, you know, you had straight on one side and then kind of a bubble, or not a bubble, but kind of teardrop shape going back to the end. That's the kind of process that this would be part of. One thing is that it has good optical quality. Since the plastic doesn't touch a mold, it doesn't pick up any defects that would be on the mold. Part is expanded by air pressure. The bubble is allowed to cool while the pressure maintains its side. Blow that air in, keep a certain amount of pressure when it reaches a certain size, let it sit there for whatever amount of time it takes to cool. There's no cooling water involved in this kind of process. That gives you your finished part. Part shape is controlled by the shape of the clamping ring through which it is blown. So instead of a mold, it has a clamping ring. Here's a picture of what that shows. It's kind of hard to really see what it is. Blowing the plastic through a opening there takes the shape of it. I know back when I was in high school, back in the 70s, a big popular item were conversion vans. You could buy these kits where either on the top or on the sides you could put these windows in. They were round, kind of half circle type windows. Pretty stylish looking windows too, I might add. And that's the way those were made. You'd blow the air through it and it would form the round circle, and then you'd let it cool, and then you'd have your plastic part. Okay, drape forming is similar to vacuum forming, and this is kind of one way that our process can be used when we use a male mold. The material is forced over the mold mechanically while vacuum is applied. In our process, really what's happening, the sheet comes out and our mold is sitting on a table with a hydraulic cylinder on it, actually air cylinder under it. So when the plastic comes in place, it's forced up, and it actually is forced up into the plastic. And then the vacuum is put on it and it sucks down around it. It can be combined with lateral stretching, which means you can stretch it to achieve biaxial orientation. Biaxial orientation means the polymer molecules are lined up in both directions. I think we talked about that when we talked about reinforcements. It can be stronger and better clarity in some polymers. One part where that's very important, it's not thermoform, it's actually blow mold. It's a process called stretch blow molding. When they make the 2-liter pop bottles, they make a preform first that looks like a test tube, and when we get into blow molding, I'll show you what it looks like. So about that long, and our 2-liter bottle is about that long. So you put it in the blow molder, there's a mechanical tube that stretches it this way, then the air blows it out this way, so you get orientation in this direction, and you get stronger total properties, better clarity, and that's very good for PET, which is used for those pop bottles. Polyethylene terephthalate is what PET is, in case you really wanted to know. Drape forming is what, when we use a male mold in our lab, is what we do. Some advantages: good inside surface definition, greater depths of draw can be achieved without excessive thinning, lower cost to make the mold than if we were using a female mold, faster cycle time. Disadvantages: more space around the mold produces more scrap. That's more the case of a male mold in the process, but that's what you get. Here's a picture of that. Material sagging, where the mold gets forced up into the material, and then the vacuum is pulled on it and it sucks down around it. Not hugely different than the other one, but just kind of a subtle difference to it. Snapback forming, variation of drape forming. The material is drawn slightly into a vacuum box below the part, again to thin the center of the part. Plug mold then used to draw it further. Finally, a vacuum applied through the plug mold causing it to snap back against the outside of the plug mold. More uniform wall thickness is achieved. Typically requires longer cycle times because, again, there's more stuff going on than just the straight processes. Again, all these variations are mainly for this, to achieve more wall thickness uniformity. That's what all the extra complication is for. And here's a picture of that. We have it's heated up and pre-stretched. It's drawn down, and then it's formed back up. The idea is to get it to stretch and thin in areas where it would normally want to be thicker, so then it kind of evens out. This isn't actually a very good picture. You can see the bubble there, and then this forces it into the mold because the mold is on top actually. The mold is forced into it like the drape forming, which was opposite direction, and then the vacuum was pulled up against it. And there's a lot of proprietary and individual variations of all these processes that individual thermoformers will use just based on their experience and what parts they're kind of running. As with extrusion and some plastic processes, there's kind of an art involved with thermoforming along with the science of thermoforming. It takes a field to get things just right, to get the thickness right, to get the temperature right, get the amount of vacuum and air pressure you need to get all that right. If you need good definition on both sides, there is a process called match die forming that actually uses two molds. There's both a plug and a cavity mold that is used, and they're not just a plug like we had in plug assist, but it's an actual mold. The molds must be matched so they fit together and leave only space for the material, so actually taking the plastic sheet and squeezing it between the two mold halves, basically. Higher pressures are used and used for parts that are more complicated and, like I said, require good detail on both sides. Like, for instance, you might make a part that has a wood grain on the outside, and maybe if on the inside it may have directions on how you would attach it to the rest of the thing you're making, something like that. Or it has to have certain texture on both sides because both sides are exposed to the consumer. But here's a picture of it. We have one mold up here, a male mold, a female mold down here, and there's just a small gap in between it, enough for the material. It can mold and put details in both sides because both sides of the sheet are being touched by a mold. And finally, there's something called mechanical forming, simplest of the thermoforming methods. The heated sheet material is formed by mechanically pressing it using forming tools, but not molds to give it shape. Not used very much. They do talk about it in the book, so I put it in here. For instance, you could wrap the heated sheet around a rod to make kind of a tube. These are forming methods. The next couple things here are two types of packaging methods that are very similar, but there's a little bit of difference between them. This one's called a blister pack, and this is for packaging of retail sales of small items. And also used in medical packaging, because if you ever go to a hospital or a doctor, everything they use, from needles to little thermometers or whatever they give you, come in individual plastic packages so that they're sterile. And then they're single-use throwaway type things. Say if you go to the store and you want to buy 4 screws. It's not like at Ace Hardware has the old bins where you just put them in a little bag, but they put them packaged, that sort of thing. They'll use this blister pack, and in this case we use a stiff plastic. The material or the part that you're buying is put into the cavity, but it doesn't take the shape of the part. It uses a stiffer plastic, and there's kind of a bubble in there, and the part's in there, and it can move around. Many of these are made at once. Usually there's a cardboard backing behind it. That's called a blister pack. A skin package or skin packaging is also used for some of the same applications, but in this case we use a piece of cardboard and the part gets put on the cardboard, and then the plastic is soft, heated up completely, and it sucks down around the part, so it actually takes the shape of the part. If you pull it off, it's usually a soft, thin plastic. There's no really cavity. You can think of as the part, and the cardboard becomes the mold that it forms around. Usually less expensive than the blister pack. You can do it usually faster rate. That covers the different types of processes. Another kind of category of thermoforming machines is what are the type of machines that are actually used. And any of these machines can use any of those processes basically that we already mentioned. The basic things a thermoforming machine needs is some method of heating up the thermoforming sheet material up to a high enough temperature where it can be formed. It has to have a clamping unit that holds the sheet in position when it's getting ready to be formed. A mechanism to raise and lower the sheet onto the mold. A vacuum system and or an air pressure system, depending on if you're doing vacuum forming or pressure forming, air pressure forming. Some kind of machine controls, which can be fairly sophisticated or very unsophisticated, as you'll see when we look at our machine in the lab. We actually use basically a drum that has little pins on it, and if you think back to what a player piano was, the little bumps on it, kind of looks like Braille, it kind of works like that. It's a very, very early, simple type of computer control system without any computer use. And there has to be some kind of safety devices so you don't hurt yourself. We'll start with the slowest and the least amount of production rate and move to the highest amount of production rate. So we have a single station thermoformer where we take a single sheet like we have on our machine, cut it to the right size, manually place that sheet into the machine, clamp it down, and this is mainly a manual process that would be used for prototypes and short runs, not for a production process unless you were making very, very large parts. If you were making big service station signs, you would make 1,000 of them. You might make 50 of them. You could do it on this kind of thing, and you make one at a time, basically. Here's a real good schematic, actually, of what our machine looks like in the lab. We have our heater back here. It doesn't show it, but there's a heater on top and a heater on the bottom. This shows the mechanism on rollers, basically, that moves the sheet into the oven and out of it. We have our mold down here. We have a bottom platen and a top platen up here. We can put a plug assist on the top. We have a hydraulic cylinder there that pushes it down, and we have an air cylinder, because there's no hydraulics on this machine. Air cylinder that pushes this up into the plastic sheet, and then a vacuum system that sucks the air through the mold and shapes the mold. We usually use it as a vacuum system. We can blow air pressure through the top there if we want to. Here is our very sophisticated cooling device, which in our lab is just a fan. But anyway, that sits on top here and blows air down there and cools it. So that's essentially what our lab station or lab thermoformer looks like. Again, for short prototype runs, maybe for large parts, of course you have a much bigger piece of equipment. That's what that would be used for. If we want to increase the production rate, we can use a multi-stage sheet fed former. We still use sheets cut into the right size. But now we have multi-stages. Things are happening throughout the cycle. When we use our single station, we put our sheet in, goes into the oven. Nothing else is happening while it's heating up. Comes out, forms, and everything takes place in a cycle. With this type, we have a loading station, a heating station, and then a forming station, loading and unloading station. So it kind of speeds up the process. While one part is heating up in the oven, we can be unloading the last part and loading a new sheet onto our loading station, and then it indexes. So it indexes one sheet into the oven. The sheet that was in the oven indexes into the forming station, so it indexes around. So you're actually doing 3 parts at once instead of a single part at once. So it speeds up the process. Now, in most packaging applications, that would be way too slow, so we need to really speed it up. One way is use a continuous roll-fed former. This is the process they use at Kerwood. Roll-fed machines are used for high-volume production applications, especially if you're making small parts. Like that lid on your coffee cup there would be made probably in this kind of process. A whole bunch of them across a wide web. The raw material is in the form of a large roll and is continuously fed into the machine. Over at Kerwood, the rolls are about 2 or 3 foot wide, and if they're sitting on the ground, they're probably about this tall. They're pretty big. They use big forklifts to move them around. The material is heated, formed, and cooled, and trimmed in a continuous operation, and it's usually highly automated. It runs through the whole process. There's usually a couple people right where the material is forming into parts. They take the parts out, inspect them, and then put them into box. It's a big, long machine. It starts out in a roll. Down here, it comes unrolled, goes through an oven. Usually, these are infrared ovens. They have very close temperature control. You can control the temperature of the center of the oven and each side, and it has several zones in it so that you can have very good temperature control, because control over the temperature helps greatly in uniform forming. So it heats up as it goes through the oven, goes to a forming station where the part is stamped out, and it continues through, and could be an automatic trim press that takes the trim material and rolls it up, chops it up so that it can be put back into the process. You could almost think of that like the old computer paper, with the little holes on the outside that would keep it going forward. That's kind of how this is gone forward. The parts come out, and then the remaining part of the web has to be ground up and reused. And even with as much optimization they do on the web, there's still quite a bit of material, maybe 20 to 30%, that has to be ground back up. And finally, if you really want to speed up your process and add to the thermoforming part of the process the actual extrusion part, instead of starting with a roll that was made at some earlier time, you can actually start with and put in line an extruder that makes the sheet material. So that's what this process is. So we actually start, the raw material input would be pellets, or could be powder. Generally pellets. They're extruded directly into a sheet and then fed directly into the thermoforming station. That would look like this. So we start with our extruder, go through a chill roll stack to make it into a sheet material, hold down table to get it in the right position, go through an oven again to get it back up to temperature, and then goes through the trim press. So now instead of starting like we did before at this point with the roll, we integrate back and start with an extruder.